Let's now turn to a situation whereby we drive the circuit with an alternating current. The EMF equals E0 times cosine omega t. Now there is an extremely important difference between the two cases. In the first case, the omega, that means the oscillating frequency of the current, was entirely dictated by R, L, and C. It imposed on the circuit its own will, so to speak. Well, if we give this alternating current sufficient amount of time, so that all the transient phenomena are died out, so that the system cannot impose anymore its own idiosyncrasies, its own frequencies onto the system, ultimately, what will prevail and what must prevail is the frequency of the driver. So the system must, when all transient phenomena have died out, it must start to oscillate at a frequency omega. Suppose I take you by the shoulders and I start to oscillate you at some moment in time with a certain frequency. In the beginning, your system will respond in a sort of erratic way, having its own sense of the frequency at which it wants to oscillate. But that will ultimately die out, and ultimately you will have to follow my frequency with which I am shaking you. The transients will die out, and my frequency will prevail. And that's exactly the same case here. So the current that will start to flow equals I0 times cosine omega t minus phi, we'll get back to this phi, and this omega is exactly the same as this omega, and it's completely independent of R, L, and C. I0, which can be derived if you solve the differential equation, is a little bit clumsy. Omega L minus omega C squared plus R squared. And we call this also Z. This thing is also called Z. This value of I0 reaches a maximum value when we have resonance. Given a value for E0, if I change the frequency of the driving voltage, I get a maximum when this equals 0, and that's the case when omega squared equals 1 over omega L, and we call that omega 0 squared. As I mentioned before, just a name. The tangent of phi, and phi indicates the phase difference between the current and the driving voltage. When phi equals positive, because there's a minus sign here, the current is behind the driving voltage. When phi equals negative, the current is ahead of the driving voltage. This equals omega L minus omega C divided by R. And I will get back to this. If I make a plot of I0 as a function of omega, then you'll see that it always peaks at omega equals omega 0. So this is now only I0, it's the maximum current, which I plot as a function of omega, and I keep E0 constant. At the value of omega, which is 1 over the square root of LC, there's no R in here, I reach a maximum, and this maximum, as follows immediately from our solution, this is 0, is simply E0 divided by R. So this value is E0 divided by R. Now since E0 is a constant, you see immediately that if I make R smaller, that I get a peak which goes higher. So this is my shorthand notation for saying R is small. And if you prefer a much larger value for R, well, capital R is large. Omega 0 is independent of R. But keep in mind that I0 maximum, which is this value here, that is independent of L and C. That only depends on R and, of course, on the value that we have chosen for E0. If we look at this solution, we give names to these quantities, omega L and 1 over omega C. We call this the reactance of the omega L is the reactance of the self-inductor. It has dimensions ohm. And 1 over omega C is the reactance of the capacitor, which also has units in terms of V. And we call this entire square root, we call that Z, and that is called the impedance. Just words, but it's useful to remember them. When omega goes up, this value becomes very large. The capacitor plates, when omega becomes large, this value becomes very small. And the capacitor plays a minor role, and L has a big effect, because if omega is large, omega L is large. Now that's immediately obvious, because if omega is large, the IDT, the change of current with time, is very fast, because that means a high frequency. And so L becomes powerful. If omega is low, then the L plays a minor role, but then the C becomes very important. In your mind, if you make omega go to 0, that means that there is almost no change in the EMF of the driving voltage. The capacitor simply blocks the current. It's like an opening in the wires. So it's very low value of omega when omega goes to 0. It's obvious that the current goes to 0. And you see that because when omega becomes 0, this value goes to infinity. And indeed you see that the current goes to 0. So it does make sense to think a little bit about the role of omega, of L, and the role of C in terms of this amplitude of the current.